Okay, armed with this information, let's try to solve example 1. And basically we're supposed to integrate the following term, dx over square root of 4 plus x squared. This is about as simple as a trig substitution can get. We notice that this obviously is of the form square root of a squared plus x squared, where a is equal to 2. Therefore, if we think about what substitution, we're going to use the a tangent theta, and a is 2, so we get x is equal to 2 tangent theta. And we're also, you notice here we've got a dx. We can't forget about that. We're going to need a dx. And if we made this substitution, we have to differentiate 2 tangent theta, and we get 2 secant squared theta. So far, so good. And now let's go back over here, and you at some point will probably memorize what this turns into. But let's go ahead and substitute in 2 tangent theta and do some calculations and see what this denominator becomes. We know that the numerator is 2 secant squared theta, and we'll put that in and fill that out in a bit. But let's deal with this denominator first. Okay, so we've got the square root of 4 plus, now not x squared, we're going to do our substitution, so we get 2 tangent theta. Alright, and we have to square that. We squared that, we're going to get a 4 and a tangent squared, so we're going to say that is equal to 4 times 1 plus tangent squared theta. But of course, tangent squared theta is just secant squared. We can bring out both the 4 and the secant squared. Let me just write this out. We can say this is equal to 2 times, I just brought the 4 out, 1 plus tangent squared is actually secant squared. I know I'm belaboring the obvious here. And then we can say, oh well, square root of secant squared, that's simply 2 times the absolute value of secant theta. And that's what our denominator is going to be. So we can now rewrite this whole term. Instead of as the above, we're going to write it as the numerator is dx. dx is 2 secant squared theta. The denominator, we've just solved for that. Here it is right here. So we plug that in, 2 secant theta. And you see how well this is going to work. This cancels with this. This cancels with this. And now, I suppose we need a d theta there, don't we? We get that this is equal to, we need to integrate only secant theta d theta. Now this antiderivative is one of those that you're just going to have to memorize. You get flashcards and work hard. And that's going to be log of the absolute value of secant theta plus tangent theta plus constant. Now, you're not done yet, because remember the initial problem was in terms of x. This is in terms of theta. We've got to substitute back in. Okay, the next step, as I said, was this x substitution replacement to get back to an equation in terms of x, but it's not immediately obvious how to do that. And the way it's always done is going back to the right triangle that we used in the example to show you where these calculations come from. And remember, in that case we said, well, imagine that we have some angle in our right triangle of theta, and opposite of it is x. The adjacent angle is, in our example, was a, but in this case a is equal to 2. And then the hypotenuse by the Pythagorean theorem is simply going to be 4 plus x squared. Now, using this triangle, we can decode any of our trig functions. So secant is the reciprocal of cosine, and therefore secant of the theta will simply be the hypotenuse divided by the adjacent. Tangent is the opposite divided by the adjacent. We can just gather them up from right here, and we get log the absolute value of hypotenuse, which is 4 plus x squared divided by 2, plus the tangent is going to be the opposite, which is x, divided by the adjacent, which is 2, and then we need to add our constant, and we're now back in terms of x, and we've solved the problem.